Hello, this is Diwakar Tiwari talking about the radiotracer technique. Before we come to the radiotracer technique, let me to introduce what is the analytical chemistry. The analytical chemistry, in a simple way, we define it as the separation, identification, and quantitative determination is called as the analytical chemistry. Separation, identification, and determination, quantitative determination, of course it is the relative term. So quantitative determination of analyte is nothing but the analytical chemistry. Any technique, analytical technique, is addressing the two important aspects, that is the qualitative as well as the quantitative analysis. Indeed, the radiotracer technique also addressing these two aspects, that is the qualitative as well as the quantitative analysis. As the name it says, the radio tracers. So the tracers are being used, or the radioisotopes is being used in the radio tracer analysis or radio tracer techniques. What are the isotopes? Isotopes, these are the nuclides having the same atomic number but different atomic masses. They are having the radioisotopes are having, since the atomic numbers are same, so they are having the similar chemical the nature or the properties. So this is the advantage that we used to take in the chemical analysis, because their chemical behavior is similar. So we used to tag with, or we used to label with the tracers. So radio tracers, and since the radioisotopes, they are the radioactive nuclides, so they undergo with the spontaneous disintegrations, or the radiations are coming out, maybe alpha, beta, or the gamma radiations. So with the help of these, the radiations, we used to trace, or we used to conduct the analysis. So radio tracers, traces, it can trace the reaction mechanism, or it can trace the chemical reactions. It's a simple way by which we used to understand the reaction pathway, the reaction mechanism, and all that can be done with the help of these the radio tracers. The other aspect of the radio tracer technique is an important aspect, that is the detection limit. At what low level the technique can be employed, because the renewed interest is that the low level detection of the analyte. The other techniques, for example, the microchemical techniques, microchemical techniques which you have studied in your UG, or even some in your second semester or the third semester the courses, there you might have used the UV visible spectrophotometer. The UV visible spectrophotometer, which can provide you the detection limit, the minimum level at what you can detect the analyte, that is 10 to the power minus of 6 gram, or 1 parts per billion. On the other hand, you will be having the atomic absorption spectrometer, the AS. AS can provide you the detection limit somewhere around 10 to the power minus of 9 gram, or 1 ppb level. This is what the detection limit, it has been shown here. This is the maximum, the low level that you can obtain with the help of these techniques. 1 ppm, it is nothing but, in a simpler way you can understand, when the solvent is the water, the 1 ppm is almost equal to the 1 milligram per liter. 1 ppb is nothing but 1 microgram per liter. On the other hand, the radioactive, or the radioactivity, or the tracer techniques, it can provide you the thousands of the atoms can be detected. Such a low value you can get, such a low detection you can have with the help of this radioactive technique. Why such a low detection is required? Because, as I told you, one of the example, if I give you, then things are more clear. Say, if Arsenic, if you want to detect in the drinking water, as the regulatory bodies, they say is that the arsenic contamination or the maximum contamination level in the drinking water, it should not exceed the 10 ppb level. So the technique which is required, which can detect arsenic much below to the 10 ppb level. So you need the technique which can detect arsenic much below to the 10 parts per billion. The radioactivity or the radioactive techniques are more useful or very useful techniques for detecting a very low level the analyte. Seabug, I can give the example. The Seabug detected some of the trans-Californian elements less than the 100 atoms in a complex material. So one of the example which we can do, that is the surface area determination of a powder or a precipitate. Surface area determination can be done with the help of the radioisotopes. A very basic principle which is involved in the surface area determination, that is when a precipitate is in contact with its the saturated solution, there is a rapid exchange of the ions between the surface of the solid phase and the solution. A rapid exchange of the ions that take place. So this exchange, this is very important to understand, this is exchange of the ions, it depends on the surface area of the powder or the precipitate. So this is the advantage that can be taken, and with the help of this we obtain the surface area of any precipitate or the powder. So therefore we can write total active atoms on surface, total active atoms in solution, total amount of substance on surface, total amount of substance in solution. How do we proceed the surface area determination? It is a very simple to understand. What we used to do, we used to take a saturated solution of the sodium sulfate, which has been tagged with the radioisotope, say for example sulfur 35 isotope is being used, whose specific radioactivity is initially known. Let the solution possesses a specific radioactivity, say S1 counts per minute per ml. One has to understand that what is the specific radioactivity. A specific radioactivity, it is nothing but the radioactivity per unit volume or per unit gram. So if S1 is the specific radioactivity, that means S1 counts per minute per ml. In this, the saturated sodium sulfate solution, which has been tagged or labeled with the isotope 35S, we used to add a known amount of the barium sulfate, say 1 gram of the barium sulfate precipitate is being added in this solution. If say the total volume of the solution was V, so rapid exchange of the sulfate ion that take place on the surface of the solid, that is the precipitate. So radioactive sulfate from the solution moved to the solid, and say SO4 with the star we used to represent it. So from the solution, the radioactive sulfate moved to the solid, and inactive sulfate moved from the solid to the solution. So this exchange that take place, and naturally a rapid equilibrium that will take place between the surface and the solid. So therefore you can write that total sulfate on surface divided by the total sulfate in solution similarly is equal to active sulfate on surface divided by the active sulfate in solution. Total sulfate stands for active plus inactive sulfate. So now what we used to do, the precipitate is centrifuged and reduced specific radioactivity. When we say that reduced activity, naturally some of the radioactivity, because exchange took place, some of the radioactivity is transferred from the solution to the surface. So if we measure the specific radioactivity in the supernatant or in that solution, if suppose this is equal to S2 counts per minute per ml, so what will be the total radioactivity transferred on the surface, that specific radioactivity, that is equal to the S1 minus of S2. S1 minus of S2 is specific radioactivity was transferred to the barium sulfate surface. So total radioactivity which was transferred, that is equal to V into S1 minus S2, and how much is the radioactivity remain in the solution, that is equal to V into S2. So now you can write a simple equation: total barium sulfate entities on surface divided by total sodium sulfate entities in solution is equal to S1 minus of S2 multiplied by V and S2 multiplied by V. So this V and this V will be cancelled out, that is equal to S1 minus S2 divided by S2. In this equation, if you see that S1 is known, S2 is known, S2 is known, this quantity is known, only quantity which is unknown, that is the total barium sulfate entities on surface. So this quantity you can calculate using this equation, and suppose this quantity it comes A. Now the total barium sulfate entities on the surface is known, and one barium sulfate surface area you can obtain with the help of the equation B is equal to M divided by D into L, where M is the molecular weight of the barium sulfate, that is equal to 223, D is the density of barium sulfate, L is the Avogadro number. So B is equal to M divided by D into L to the power 2 by 3. If you put all these values, one can get the value of B. Once the total number of entities A is known, one entity's surface area is known, so total surface area one can obtain with the help of this equation, that is equal to A into B. So this, the radiotracer technique, can be employed, can be used for determining the surface area of solid or surface area of the precipitate. The other example is that the direct isotope dilution analysis, DIDA, direct isotope dilution analysis. This is a very simple way of performing this analysis. The basic principle of this is that the total radioactivity is conserved. That means that the initial total radioactivity is equal to the final total radioactivity. Suppose you will be having X gram of compound which you want to analyze, and its radioactivity, specific radioactivity is 0. Naturally it is non-radioactive. What we used to do, we are adding Y gram of the labeled compound that is having the radioactivity of say Si. This has been added with this X gram of the unknown compound, and then we used to add the total mixture X plus Y gram. We try to get its specific radioactivity. Suppose it comes SF. So the total initial radioactivity will be X into Z0, Y plus Y into Si, that is equal to Y into Si, X into 0 is equal to 0. So this is equal to the final radioactivity, that is equal to X plus Y multiplied by SF. So from this equation, X is equal to Y into Si minus SF divided by SF. So you can calculate the X, how much was that the unknown compound. Similarly, the inverse isotope dilution technique we used to use, it is simply the inverse of the isotope dilution analysis. Here what we are having, if we will be having X gram of active compound having the specific radioactivity is Si, this we want to know that how much is the X gram in that sample. So Y gram of the inactive compound is added, that is equal to the 0. So total amount is now in the mixture is X plus Y gram. Suppose its specific radioactivity is SF. So again we will write the same equation, that is the total initial radioactivity will be equal to the total final radioactivity. So the total radioactivity, initial radioactivity will be X into Si. Why we are multiplying is X? Because Si is the specific radioactivity. When you multiply it by the total amount, that is the total grams, then you will be getting the total radioactivity. So X into Si plus Y into 0, that is equal to 0. This is the initial radioactivity. Initial radioactivity now naturally it is equal to X into Si is equal to X plus Y into SF. From this equation, if you try to calculate the x will be equal to y into SF divided by Si minus SF. In this, y is known, SF is known, Si is known. So you can calculate x. So using this equation, you can conduct this inverse isotope dilution analysis, by which you can analyze the analyte which was radioactive, that is the X gram. Now I'll come to the next, that is called as the neutron activation analysis. As the name says, it is based on the activation by the neutron, the analysis. The analytical technique, this is a very useful technique, widely being used for the biological sample, agricultural sample, chemical analysis. Lot of applications are there of this neutron activation analysis. The neutron activation analysis was first discovered in 1936 by George Charles de Hevesy from Hungary and Hilde Levy from Denmark. The neutron activation analysis, of course, it is very sensitive, very low level detection can be done, and not only the low level, it can be used for the multi-element analysis also. It addresses, as I mentioned initially, the qualitative as well as the quantitative analysis of many major, minor, trace and rare elements. The neutron activation analysis is a kind of the non-destructive analysis. What do you mean by the non-destructive analysis? The non-destructive analysis in which the sample is not being destructed. What happens? The other techniques, say for example, the atomic absorption spectroscopy, ICP-MS or ICP-OES, the inductively coupled plasma analysis, there what we used to do, we used to dissolve the sample and then we used to analyze the sample for a particular analyte. So what happens once analysis is over, the sample one cannot get the sample back, so you have to destruct that sample. But with the help of this neutron activation analysis, the sample can be taken back, it cannot be destructed. This is, you must be knowing some other techniques, non-destructive technique, for example, X-ray fluorescence spectroscopy. You must be knowing like the X-ray photoelectron spectroscopy. These are also kind of the non-destructive analysis. Of course, the basic principle is quite different. So neutron activation analysis, it is kind of the non-destructive analysis. For some of the samples, say the gold sample, say the precious stones, you don't want to lose the sample. So these kind of the non-destructive techniques are more useful. If you look at that, the neutron activation analysis, it includes a wide range of the elements that can be analyzed with the help of the neutron activation analysis. Wide range of the elements that can be analyzed. The basic principle of the neutron activation analysis is by the N-gamma reaction. N-gamma reaction, that means that if you will be having a target atom X, which can be irradiated by, X is the target atom, has been irradiated by the neutrons, and with this schematic it is more easy to understand. This is your target atom, say X, having the Z atomic number and A is atomic mass, is the neutron, which is called as the projectile. With this projectile, this is being irradiated to the target, and this can be captured by this target. The nucleus can capture this neutron and forming the compound nucleus. This compound nucleus, which is highly unstable, it undergoes with the prompt some gamma radiations, and followed by the beta emission that will take place, and then you can see that the nucleides undergoes with the the gamma decay, the gamma radiations are coming out, that can be detected with the help of this, the detector, and the daughter nuclide is being formed. So here, this is a highly unstable nuclide, and that undergoes with this gamma radiation. So these gamma radiations are being detected. So that's why it is called as the N gamma reaction. X is the target atom, N is the projectile, gamma is the ejectile, Y is the daughter. So with this, with the help of this, we used to conduct this neutron activation analysis. We used to activate the nuclide with the help of this, the neutrons. So in this, the principle is that if suppose you have if suppose you will be having, let x gram of the sample containing n atoms of the element which you want to analyze. So what we used to do, we are taking the sample in the neutron source, irradiating it, say for example for the time t, and then the total radioactivity generated, that will be equal to AT into n into phi into sigma multiplied by 1 minus e to the power minus of lambda t. What are the terms? The terms, AT is the total radioactivity generated, N is the number of atoms present in that analyte, or the analyte and the element which you are going to detect, the total number of atoms in that complex matrix. Phi is the neutron flux. Neutron flux, that is the number of neutrons per centimeter square per second. Sigma is the neutron capture cross section in centimeter square. One has to understand the meaning of this neutron capture cross section. Neutron capture cross section, it is nothing related to the geometric cross section. It is something different from that. It is the nuclear reaction cross section. Nuclear reaction means that the probability of the nuclear reaction to take place, then the probability of the neutron to capture the neutrons. I can give the one example. Say in the nuclear reactor, we are using, the fuel is uranium-235 as well as the uranium-238. Uranium-235 is capturing the thermal neutrons, and uranium-238 is not capturing the neutrons, the thermal neutrons. So now the question is that what is the probability? The probability of capturing the thermal neutrons by uranium-235 is very high. So that's why the neutron capture cross section is very high for uranium-235, and it is very low for uranium-238. So one has to understand this is the probability of the nuclear reaction to take place, or probability of the neutron capture to take place. So that is represented in the cross-sectional area. And lambda is the decay constant. So all these terms are known, and one more term, the quantity A is equal to, as you all know, A is equal to N into lambda. N is the number of atom, lambda is the decay constant. From this equation you can write N is equal to A by lambda. We can write the same equation, N is equal to AT by phi sigma 1 minus e to the power minus of lambda t. However, there is the problem, or I can say that another quantity which has to be obtained, because you cannot get the radioactivity immediately after the irradiation is over. If your sample is irradiated, say for time t, immediately after that you cannot, it's not quite possible to measure the radioactivity. There is a time lapse. Time lapse, suppose this is equal to t dash, until you measure or you obtain the radioactivity, because you have to take the sample from the reactor and then you have to take it to the lab where your counters are there and you are measuring its radioactivity. During this process, suppose the lapse of the time is t dash. So now the total radioactivity, based on the decay constant, you see that you must be knowing this equation. AT is equal to, decay law says that AT is equal to A0 e to the power minus of lambda t, where you have to understand where AT is the after the time lapse, that is the radioactivity at time t is the AT, A0 is the initial radioactivity, lambda is the decay constant, T is the time of the lapse. So here I can say that the lapse of the time is T dash, AT dash, this is again AT dash, A0 is nothing but it is AT. Now AT dash is equal to AT e to the power minus of lambda T dash. One has to understand what is the meaning of T dash and what is the meaning of T. T is the total time of irradiation for which you have irradiated the sample in the reactor with the help of these neutrons. T dash is the lapse of the time once you have taken the sample from the reactor and to the counter, the time which has been taken from taking the sample from the reactor to the counter. So AT dash, now if I put AT dash is equal to, as I have written here, AT dash is equal to AT into e to the power minus of lambda t dash, I'll put the value of AT from the previous equation, that is n phi sigma 1 minus e to the power minus of lambda t into e to the power minus of lambda t dash. Here, if the weight of the sample is W gram of the particular element present in the X gram of the sample, so W is always equal to the Avogadro number L and the atomic mass M divided by the Avogadro number L. W is equal to total number of the atoms N multiplied by the atomic number divided by the Avogadro number L. So if I put the value of N in this equation, this is equal from this equation. So M by L multiplied by AT dash divided by sigma into phi into 1 minus e to the power minus of lambda t into e to the power minus of lambda t dash. In this equation, now you see that if phi is constant, L is constant, sigma is constant, and then the time duration is constant, then W is directly proportional to AT dash. So with the help of this, what we used to do, instead of using this complicated equation, what we used to do, we used to take a standard having a known amount of the element. We try to take a standard having a known amount of the element W0 and the other unknown, say it is W. So W, since W is directly proportional to AT dash, so W by W0 is equal to AT dash by AT0, where AT0 is the radioactivity for the same period when it was irradiated, the total radioactivity, and lapse of the time is also the same. So the total radioactivity is AT0. So from this we can calculate the value of the W, since AT dash is known, AT0 is known, W0 is known. So W can be estimated with the help of this equation. A large number of the samples or the large number of the samples can be analyzed, say W1, W2, Wn, all that can be analyzed. Not only that, the other elements also can be analyzed with the same irradiation, but the same, the same element which you are going to analyze, the standard for that element that has been required. Some of the examples which we can provide here, say chromium content in a ruby, which is a combination of the alumina and the chromium. In this, the chromium is present around somewhere 0.1 to 0.4%. So that can be analyzed. So chromium is being, 50 chromium. That is, with the help of this N-gamma reaction, it has been converted into the 51 chromium, and then this chromium, this radioactive chromium this is a gamma emitter that can be analyzed, and then the chromium quantity can be obtained. Similarly, the manganese content in the tea leaves, where the 55 manganese is being converted into 56 manganese having the half-life period of 2.58 hours. This is again the N-gamma reaction. Usually it comes somewhere around 0.13%. The arsenic poisoning, it comes in the hair. So here we used to analyze with this the neutron activation analysis, that is the N gamma reaction that take place. So arsenic 75 is converted into arsenic 76. Arsenic 76 is radioactive, having the half-life period of 26.3. So this gamma radiations which is coming out, that is being analyzed. So these are some of the examples in which, say, chromium in the ruby, manganese in the tea leaves, arsenic in hair, all these can be analyzed with the help of this, the neutron activation analysis. A large number of the applications are there where the neutron activation analysis is being used. This is one of the non-restrictive analysis. This has been the multi-elemental analysis can be done, and it is quite efficient and very accurate. So that's all. Thank you very much.